right, so now we move on to lesson 3.2, which is actually the final lesson of unit 1, which we call chapter 3 of our quadratic function unit. And what we're going to deal with is we're going to deal with quadratic functions in general form and how we can solve them not only graphically, but how we can pull a piece or apart all the elements that we need, including things like y-intercept, the vertex, the x-intercept, and then provide them in contextual problems of, well, what happens if we provide some sort of blurb around them and some sort of real world scenario around them, and then we say, based on that and the quadratic function it creates, what type of information can we pull from it, whether it be the vertex, the y-intercept, or the x-intercept, and what those things mean in real life when we graph these things. All right, starting off with number 1 here. Or part 1, I should say. What we want to do is we want to specifically look at the equation in general form. Now, general form, it differs from vertex form because when we look at general form, it has this more traditional trinomial look, or the y equals ax squared plus bx plus c, or because we know f of x is equal to y, I mean, these technically mean the same thing here. Now, the important thing is that a, b, and c, in terms of the coefficients, are real numbers. A cannot be equal to 0, or else this thing would be a quadratic. And then when we look at the c value, this is really important. The c value is the y-intercept of the graph. And when we say f of 0, essentially what we're saying is that when the x value is 0, it eliminates those first two terms that have x in them. The b and the a, x squared, go away. And we look at this and we see that we only get the c value. So anytime we see c in this general form, think that's your y-intercept, and it will help us out from here. Now, let's begin with example 1 here, where we're going to identify some characteristics given the graph and its equation that pairs with it. All right, so here's the graph. Direction of opening. Well, we can clearly see that the tails are facing downwards in this situation. So what we're going to do is, for our first box, direction of opening, simply we're just going to write that it is down. What are the coordinates of the vertex? Well, we scroll over here, we see that the highest point, or the maximum, occurs here. And remember, it doesn't have to be a maximum. We could also have a minimum in terms of quadratic functions, but it just so happens this one faces down. I'm going to write this as 1 for x and 8, or not 8, but we want to make sure this is 9 because it's 1 unit higher. So that means that our p and our q, which represent the vertex, are going to be 1 and 9. There we go. Do we have a minimum or a maximum value? Well, we clearly have a highest point, so we call this a maximum value. And it's a maximum value where y is equal to 9. Remember, it's always the q value of our vertex. The equation of the axis of symmetry. Well, the equation of the axis of symmetry is simply the x value at the vertex, which in this case, it is symmetric about the x equals 1. And what we could do is, on our graph, if we wanted to, we could draw a dotted line right down the middle here, and we could indicate that where x is equal to 1, this is actually that line that creates the symmetry to left to right. All right, now going down here to our x-intercepts, if we look at our graph here, we have actually 2 x-intercepts. We have 1 x-intercept over here, 1 x-intercept over here. We're going to just generalize that this is 4 and 0 for now. On the other side, we're going to generalize that this is negative 2 and 0 for this x-intercept. So we have 2 x-intercepts that we're going to write here. X is equal to negative 2, and x is equal to positive 4. And we could write them as coordinates if we wanted to. That's another popular way, or in fact, almost somewhat the more correct way to write these. But if you write them on the graph like this, and then x equals negative 2 and x equals 4 over here, that's okay. Our y-intercept, that's our next piece we want to do. Well, that's actually right here. That's going to be at 0 and 8 for f of x, or for y. So we're going to go over here and write y is equal to, and we're going to write it as 8. And again, we could write the coordinates, but I'm just going to write the coordinates on the graph as we have them there, and that will be okay. And then the domain and range, well, in the case of this one, if they give us a general quadratic equation, we know that the element of the reals is going to be for the x's because they extend to the left and right to infinity. Now, that will change at the 30 level, but for now, our domain is quite simple when it comes to these functions here. We're going to write it as domain with the curly bracket and say x such that x is an element of all real numbers, because it's technically an infinite amount of solutions. The range, well, we know that there's a highest value of, in this case, 9. So we're going to say y such that y is less than or equal to that 9. Once it's past 9, it can realistically be any number in the real plane, which we write as y(er). Okay, so now we have all these elements: domain, range, we have our x and y intercepts, we have our equation of the axis of symmetry, direction opening, vertex, max minimum value. This can all come together very easily because when we're given the visual, I mean, it's just identifying them and putting the specific points into action here. Okay, comparing vertex form and general form. What we're going to do in this piece here for section 2, we're going to expand the vertex form and then compare it with the coefficients of f of x equal to ax squared plus bx plus c, or the general form, and just see when we expand vertex form generally, what coefficients compare. And so we're going to do it in the following way. I'm going to substitute y into f of x, which is equal to a. Remember, when we square a term, that's going to cause the binomial to be written out twice, not go squared to this and then squared to this. We're going to squared means I write this out twice. So I'm going to write it as x minus p times x minus p and then plus q. When I expand this out, it's going to give me y is equal to a. In the brackets here, I have x squared minus xp plus p squared, all with q on the outside, because that just remains on the outside of this expansion. I'm going to then simplify this as y is equal to, we're going to not only collect these internal terms, I have 2 of these negative xp's, I'm also going to expand the a into all the terms here. So this is going to become ax squared negative 2a px. I'm going to make sure I write the x last. Then I'm going to have plus p squared, or in this case, I need to make sure I have my a on it, ap squared, and plus q. And again, where did I get this fact that there was 2 of these? In the case of there was 2 negative xp's here. And then the reason I write the x here is because I want it in terms of a coefficient with an x term. Coefficient and an x term. All right, now what we're going to do is we're going to write the general form right below this. General form is ax squared plus bx plus c. Now this makes it very easy because we're just going to highlight the coefficients that are similar. A in front of the x squared is the same, so that's kind of nice. We can connect those with a solid highlight and be like, these are similar. Our negative 2ap is the same as b, so we can highlight those two and compare them together. And then lastly, the constant term, where everything without an x on it is just the c value. So these would all be tied together. And as you can see, we've left the x squareds alone, and then we've also left our simple x to the power of 1 alone. And we just talked about the coefficients and their values. So generally, if we had any sort of specific values, I mean, we could plug them in here, but generally this is the a, b, and c in terms of general form when we expand vertex equation. Okay, now flipping over to number example 2 here, what we're going to look at is they say the x-coordinate of the vertex can be given by negative b over 2a. Use this information to determine the vertex of the quadratic function y equals 5x squared minus 15x plus 7. Okay, this is interesting because what we need to do first and foremost is when we see an example like this, you're probably thinking like, where does this come from? Because they're telling us this negative b over 2a is the x-coordinate of the vertex. It actually comes from calculus. And so I would never make you prove this, but let's just do this very quickly off to the side. If I know that the original function is f of x equals ax squared plus bx plus c, then when you get to calculus, you're going to learn that the derivative of the function of x, or the first derivative of f of x, is equal to, we multiply this as 2ax plus b. Now, again, you will not have to do calculus or derivatives on this, so don't feel like you have to derive this, but I'm just going to show you what this is doing. Now, verbally, when we take the derivative, what this actually does is we're figuring out if we have the f of x and this is the derivative it's equal to, that means I can technically find the tangent line at any point on the curve. So if this was my parabola like this, then using the derivative, it allows me to draw some sort of line tangent to that curve. And realistically, that tangency can exist anywhere. But what we're going to do is we're going to say, suppose that the function aims up like this. In order to get the vertex value of x, we're going to take the tangent or the derivative right along the bottom. Now, when we do this, what this actually does is it allows us to get the absolute minimum here, or maximum if it was downwards facing, but it's upwards facing for this graph because of the positive a. And if we take the tangent along the bottom, the slope of the line that is tangent is 0. So we're going to write this as equal to 0. We're going to continue this off to the side here. If we know that this is 0 is equal to 2ax plus b, I'm going to subtract b originally, which gives me 2ax left behind. I'm going to divide both sides by the 2a, divide both sides by the 2a, and then therefore, I'm going to arrow up here, therefore, we get an x value which is equal to negative b over 2a. So the tangent line that exists at the minimum point here is where x is equal to negative b over 2a, or the x value when its tangent is this. So again, you will not have to do calculus. You will not have to prove this. Hold off until you get there, until math 31. But for now, just trust that we're taking a derivative, and that's how we can derive this. Now, when they say use this information to get our x, well, simply put, what we're going to do is be like, okay, let's identify the a, b, and c so that we can plug it into this formula that they gave us or that we just derived, and then we can solve for the x. So step number one, if we know x is equal to negative b over 2a, then let's actually just identify the a. The a is equal to 5. It's the first coefficient, or the x squared coefficient. The b is equal to negative 15 because we take the sign with it, and that's the one that's in front of x. And then c, or the constant term, is equal to 7. Now, if this is the case, let's just plug these values in. Negative b, we're going to make sure we plug in the negative 15 here because the negative out front of the equation is already there. Divided by 2 times the a value, which is 5. This is going to give us negative negative is a positive 15. Divided by 2 times 5 is 10. When we reduce this, this is going to give us 3 divided by 2, or we could write it as a decimal of 1.5. Now, this hasn't actually given us the value fully yet. If we know that this is what the x value is at the vertex, they want the full vertex. To get the full vertex, what we're going to end up having to do is we're going to have to plug this 1.5 back into the original function where y is equal to this portion here. Now, let's just do that right below here. I'm going to go y is equal to, and we're going to plug it in. So it's going to be first and foremost 5 times the 3 over 2, which I'm just going to write as 1.5 squared. We then have minus 15 times 1.5, and then plus 7. If we do this in our calculator, let's actually just pull this up here. I'm going to bring open a calculator here. So first and foremost, we had 5 times the 1.5 squared. Then we had minus 15 times the 1.5, and then plus 7 here. Perfect. So we get negative 4.25. I mean, we could write this as a fraction as well, negative 17 over 4. And so let's go back to our notes here. We're going to write this as negative 4.25 or negative 17 over 4. And just to confirm that value, I want to go back and make sure. Yep, negative 17 over 4, which we can't reduce anymore. So therefore, if we write our vertex as a summary, therefore, we have a p and a q, which the p value is going to be 1.5. The q value is negative 4.25. And that would be our solution there. So use the information they give you, identify your ABC, and then once you get an x value, plug it back into the original equation. Awesome. Okay, let's go to example 3. They say for these ones, how many x-intercepts does a quadratic function have in the following conditions? As soon as they give you a question like this, what I want you to be thinking is, I must draw out a basic Cartesian plane. Something very, very basic, just like this, where it's like x and y, and we write it where we want to make sure we just have these standard coordinate planes or the standard Cartesian so that we can sketch a rough sketch of what this situation is. An axis of symmetry at -1. I'm going to go to -1 and put a dotted line that goes up. So I'm going to try to make it like that. There we go. And I'm going to write this as x is equal to -1. That's the axis of symmetry, or the line that divides this in half. They also say that the range, or the y values, must be greater than or equal to 0. So I'm going to start right here, and then I'm going to aim it upwards, or make my arms go in the upwards manner, because when we look at this, in order for it to be greater than or equal to 0, it must be an upwards facing graph. How do we know it starts at this point? Because they said it could be equal to 0, but it must be greater. Therefore, you would say, how many x-intercepts does this have? It only has the one right here at the very bottom, or at the minimum point. So therefore, we have for x-intercepts, and I should just phrase it as, there is one x-intercept. Awesome. There we go. Okay, let's go down to our next example. So again, we're given new conditions. So what we want to do is draw out another Cartesian plane. I'm going to draw out the x here. I'm going to put my y here. And then what I'm going to do is I'm going to start by dealing with the vertex at -4 and -2. So -4 would be somewhere about here. -2 would be somewhere about here. Now, let's put our point here. The y-intercept is negative. This one is interesting because there can actually be two possible cases. The first one is in blue. What if I drew my graph like this? Here and then here, so it's quite flat, but it extends upwards. Well, you would say, based on this, if I was to extend my x-axis, which I'm going to do that right here, you would see that this is two x-intercepts. So therefore, we can have, there are two x-intercepts. But we're not done yet. That's for this case. What if it faces upwards and it crosses through the y-axis? Well, the y-axis is negative here, so it still is possible that this is the case, but we also have a different case. We could also have a graph that faces down like this. And if it faces down, will it ever cross the x-axis? No. And in fact, let me go back here and use my laser pointer instead. If I look at this, I see that it never crosses the x-axis. If I'm the green graph, it faces down, it's only going to go downwards to infinity from -2. How many x-intercepts in this situation? Well, there's actually 0. So, or there are no x-intercepts. And let me just make sure I clean that up a little bit. There we go. Perfect. So there's actually two options here. Either we have two or we have none. And that's the different options here. So if we look at these in like the grand scheme of things, the options are you either have one, you either have two, or you have 0. Those are the options we have at play with quadratics. Okay. Now, let's move forward to example 4, where they're going to get us to sketch 1, and they're going to say, given the sketch or given the situation of this description of it, can we label points based on this? And then can we write the equation based on the graph that we construct? Okay, let's start off with the first detail. Axis of symmetry at 1. Okay, axis of symmetry at 1, I want you to put a vertical line. This is the part that divides the graph in half, where x is equal to 1. And what I always recommend is write the actual x value below that represents the symmetry line, just so that people know that's what that line means, and it's not just some random dotted line. They then say we have a minimum value of +2. Well, the minimum value actually occurs on this axis of symmetry because the vertex, whether it be a maximum or a minimum, occurs on the axis of symmetry. In this case, there's a minimum of 2. So we look at this and say 1, 2. We have our first point right here. Now, we want to label some of these other points. They said it passes through -1 and 6. Well, -1 is right here. 6 is 1, 2, 3, 4, 5, 6. So right up here. So we're going to put a dot right here. And what I'm going to start by doing is just labeling these points here. This one was -1 and 6 for y. Our vertex point was equal to +1 and 2, which is our minimum point. And then here's the interesting thing is we know that if this is the axis of symmetry and the -1 and 6 is on the graph as some sort of point, then by symmetry, if I go 2 units to the right of the axis of symmetry at the same height, I find the third point that I can put here. And this is going to be at +3 and 6. Now what I can do is, realistically, I could draw more points, but what I'm going to do is cap it at that, and I'm going to sketch it with the arms going through those points with arrows on the end representing that this goes on to infinity. We're not in the real world situations yet, so we want to say that this will go to infinity. Okay, we've sketched as much as we can based on the information, labeled the coordinates of the points we know. We just did that, but let's just make sure we list them out here. The first point was -1 and 6. Our vertex point was going to be at 1 and 2 for y. And then our secondary point, or our third point, I should say, is at 3 and +6, which was the mirrored image of the -1 and 6, but on the right-hand side of the axis of symmetry. Now they say write the equation in quadratic function in both vertex form and general form. Well, we want to start with vertex form because in reality, we have a point and a vertex. We actually have 2 points and a vertex, but we're going to choose to use one. Maybe let's choose to use this point and this point, or the vertex and some sort of x and y. Okay. And I may even write that below just to help us out here. So this is going to be our P and our Q, which is our vertex. And this is going to be our X and our Y that we're going to use. Okay, let's scroll down here. So let's start by writing out the vertex form equation. Y is equal to A, X minus P, all squared, plus Q. Remember, we always must solve for A. We don't know what the stretch factor is or the vertical stretch factor, so we must solve for this right away. That was my biggest recommendation when we talked about this in class. Now what we're going to do is we're going to plug in our X and our Y. For the x and y, we chose to use the point that is on the right-hand side, so 6 for y. So I'm going to plug in 6 is equal to a 3 for x minus p. Well, if it ended up being on the right-hand side of the positive line, or it's on the positive x's, it actually means it's negative in the bracket, meaning this is negative 1 squared. The q value is 2, and we don't do any sort of sign flip with that one. Now let's simplify this. 6 is equal to a. 3 minus 1 is 2 squared plus 2. I'm going to subtract away the 2 from both sides. When I subtract away the 2 from both sides, I get 4 is equal to a. 2 squared is 4. I divide by 4, and I divide by 4. This is going to give me a is equal to 4 divided by 4, which is just a equals 1. Now again, you're like, wait a minute, why are we even solving for a? Like, what's the point of that? If a is just 1, doesn't that just mean it's the original stretch factor? Yes, but we don't know that until we solve for it. So I highly, highly recommend we make sure we solve for that first, always. Okay, from here, we're going to write out our equation. Therefore, y is equal to 1, which is a. We don't really need to write that in. X minus 1 all squared plus 2. And again, when we talk about horizontal translation, this actually means we go 1 unit right, which puts us at positive 1. So just to reemphasize that, and then no special tricks around the 2. Now let's highlight this because this was part of the equation they asked for. They said, what is it in vertex form? But then they also said, what is it in general form? So now what we have to do is we say, let's expand this. Y is equal to, anytime we have a binomial squared, we want to make sure we write it out twice. X minus 1, and then the plus 2, which is the q value, stays on the outside. When I expand this, it's going to give me x squared minus 1x plus 1 plus 2 on the outside. Now we want to combine our like terms and write this as general form is equal to x squared. We have 2 negative x's. 1 plus 2 is equal to positive 3. And there we go. There is our function in general form. Now, as a way to just kind of like confirm something here, and if we've sketched this out right, we might have sketched this out a little inaccurate, so that's okay. But we know that the c value in the general form means the y-intercept. And so if I go up to my graph, realistically, my graph should intersect right here. That's just a bit of an like an inaccuracy when we drew this. No problem at all right now, at least. But we should have cut through here, kind of almost like this, and then went through the point like that. That would be probably the more appropriate drawing. But you know what? We're not going to get super nitpicky with that. As long as these are your two forms, we're totally fine. Okay, now here's where we shift into part 2, and this is where we're going to do a ton of calculator work. And so be prepared for me to do some verbal explanations, and then have your calculator right next to you as you're doing these problems, because you're going to want to type these in for yourself, especially just to make sure that you can get the proper window that I'm describing in all these problems. Okay, these problems are going to look very familiar. You're going to look at these all in surface level and be like, haven't we talked about similar problems? We have. When we talked about completing the square, we actually talked about very, very similar circumstances. It's just going to be a little bit different in terms of the way we think about these and the way we solve these, because now we're just purely using our graphing calculator and the general equation. Okay, example 1. Suppose you were on a cliff and you're standing 110 meters above the beach. You throw this stone straight up and it goes up in the air a little bit, and then it falls to the beach down that 110 meters from the original position you're at. Now, of course, we're not going to do physics 20 in this. We're not doing projectile motion. So what we're going to do is I want you to take this function here, this h of t equals negative 4.9t squared plus 17t plus 110. And I want you to just rewrite this in a following way so that when you plug it into your calculator, you can do this. Under y1, which is going to be under your, for my TI users, the top left button, y equals, you're going to put negative 4.9. And instead of t squared, you're going to put x squared. The next term was 17t, so we're going to go plus 17, and instead of t, we're going to write x. And then lastly, we're just going to write in our constant term of 110. Now, when you click graph, what this might show you is if you have the original window settings, it's actually going to throw you off a little bit. You might not be able to see the whole thing. So here's what we're going to do. In order to build the graph, I want you to put in the following settings into your calculator. Here is x, here is y. So as we look at this, it always goes in the following format for both these brackets. A minimum value first, a maximum value second, and then the scale or SCL as our third option. Now, one recommendation I'm going to make when it comes to any of these real world application problems is, in general, what we can always do with these is we can set our x minimum to -5. We can then set our scale to 1. Under the y's, we're going to do something very similar. But instead, I'm going to give us a little more space. And don't worry, I'll explain these in a second. -10 for y, +1 for the scale. Which scale just means that every unit that goes by is 1 unit, or every tick is 1 unit. And it just kind of helps us. You can adjust this if you want, but I think for consistency at the 11 level, it sometimes is easy just to put 1 for these. Okay, now for the next piece here, what we're going to do is we're going to say, well, if this represents the t values or the x values for us are representative of the time in the function, then when you throw an object off a cliff, it typically doesn't go for a very long time. And so what we're going to do is we're going to set our x max to about 10 seconds. Because realistically, I don't see this object being in the air longer than 10 seconds unless the height was just so large that it's going to hang in the air for a long time. Gravity's going to be pulling on it. So we're going to set it to 10 seconds for the maximum. For the y value, I'm going to set this equal to, we're going to look at our original equation and say, well, if this value right here, or the constant value is 110, this is always our y-intercept. So this isn't even the highest point. When we look at this, this represents some portion on the way up. And if that's a portion on the way up, I'm going to set the value to about 150. And I'm going to hope that if I set this to 150, it will encapsulate that maximum that we're looking for here. Now, here's our window settings. So we have min, max, and scale for both our x and y. And now what we're going to do is just provide a sketch of it. So you're going to graph this. Now, if you have a Casio, you're going to want to go into menu, graph, and then type in this y1. And then you can simply just click graph after this or draw on the Casio. What we're going to do is it's going to look like this. I'm going to do a very, very rough sketch. Here's our lines. We set our maximum up to this value here. So we said a window of 150. We set the x max to be at 10. So I'm going to write 10 over on the far side here. And then what we found here is that the graph would look something like this. It's going to kind of cut through here, make some sort of parabolic shape, and then come back down. Perfect. And I'm going to actually use my proper sketching tool so that this looks a little neater. So it kind of looks like this. There we go. Okay. Now, yours might look a little different, but overall, if we have these window settings, it should look approximately like this. Now, what we want to do is answer the questions based on this rough sketch and see what information they want us to figure out from here. First and foremost, what is the y-intercept and what does it represent? Well, just like we said before, the constant value in the general equation is the y-intercept. So let's actually go and label that on the graph here. I want you to put a dot here, and then I want you to write in the point 0 and 110. And then just make sure you draw an arrow to that point if it's not right next to it. Now, if we know that the y-intercept is 110, what does this represent? Well, the y values are the h of t's. Realistically, we could even write that in here. This is our h of t, this is our t-axis. It's how far we start in the air, or where we start in terms of how high are we above on a cliff from the beach. So let's make sure we write that in the sentence here. What is the y-intercept? The y-intercept is 110. What is it symbolic of? It is the starting height. Of the thrower. And you can even say it's like the original position if you want, but that's okay. And then, so we can say therefore it is like 110 meters if we really wanted to. That would also be okay, just to kind of throw that in there. Now, what is the maximum height that the stone reaches? In order to do this, we're actually going to have to do a bit of calculator work with this one. So when we look at this piece here, what is the maximum height and when does it occur? We want to look at our graph here, and we're like, that means we're solving for the vertex up here. Well, in order to do that in the calculator, let me just write out the steps, and then I'll help you visualize kind of what those steps look like when we actually take it to the graph here. So for my Casio users, or for my TI users, let's start there. You're going to go second, or the blue button, trace, which is the fourth button on the top, and then you're going to click maximum. Now, the reason we're selecting maximum is because there's a highest point. Now, more about this and what to do with this in a second. For my Casio users, you're going to click Shift. You're going to then click G-Solve. and max. Perfect. Now, for my Casio users, as soon as you go shift G solve max, it's actually just going to give you the value right away. It will give you the X and Y or the P and the Q that represent the vertex. Easy peasy. For my TI users, what you're going to have to do is on the calculator, what it's going to do is when you go second trace and then you look for this maximum, you're going to have to select somewhere on the left, so somewhere about here, click enter. You're then going to have to select over here and move your cursor to the right, click enter. Lastly, it's going to ask you to guess. You want to put it as close as you can to this maximum point. Now, when you do that in your calculator, here's what it gives you. Rounding to 2 decimal places, I'm going to get 1.73 and 124.7. Okay, and again, you may want to just write an arrow over to that point there. Okay, now that's our vertex, so let's make sure we go down and we'll write it here. What does the vertex include here? It's a P and a Q, where the P is equal to 1.73 and the Q is 124. Let me make sure I fully write that in, 124.7. And then what is the maximum height that the stone reaches? It's actually the output value. It's the Q value. So we're going to say the maximum height. Whoops, let's make sure we keep it here. Maximum height is 124.7. And not only 124.7, but 124.7 meters. When does this occur? It's always the P value, or this is the amount of seconds it takes in order to reach the maximum height. So we're going to say it takes 1.73 seconds. There we go. Okay, now let's go down to our next piece. How long does it take the stone to hit the ground? Well, graphically, let's actually just go and take a look at what that actually means here. If we know that we start here at the 110, this is on top of the cliff. It goes up in the air, and then down here, right here is the beach. This is the piece we're looking for. And what is this technically called on a graph? It's our x-intercept. And so in order to solve this, let's actually just write out our steps below, and then we'll provide a value on our graph here. How long does it take to hit the ground? Here's our steps for this. TI users, second, trace, x-intercept, or in this case, it's going to be 0 for my TI users. So you're going to click second, trace 0. More on this in just a second. For my Casio users, you're going to click shift, G-solve, and then you can click x-intercept. Or on some of the models, and more often than you're going to see it, I should actually just write in 0. But in your model, if it is x-intercept, then you'll want to put x in. Okay, now let's provide the value here, but explain what we need to do with our TI calculator in order to get it. So just like when we solve for the maximum, the TI always wants you to do a left bound. So somewhere about here, I want you to bring your cursor there and say, this is your left bound, click enter. I then want you to go a little bit below here on your right-hand side, shift your cursor here, press enter. Then when it says guess, bring it as close as possible. Now, when we solve this, what we're going to end up getting is that the x-intercept is 6.78 and 0 for y. There we go. And we're going to put an arrow to that representing that this is the point we're looking for. And so let's make sure we write that below, and then I'll provide a little bit of a summary based on that. So what is or how long does it take to hit the ground? Well, that's our x-intercept. And our x-intercept was equal to 6.78 and 0. Therefore, it takes 6.78 seconds to hit the ground. There we go. Okay, now let's go up and just explain something before we go into the domain and range and anything further. I just want to go up here and talk about why we set our certain function parameters to what we did. So in terms of why did we set our window settings as X and Y to what we did? If we look at this, if I didn't include this as -5 and I didn't provide any space on the left or the negative x-axis, we would look at this and simply see it as purely cutting off right here, and it would be very hard to see the y-intercept. So because the y-intercept is so significant to the problems and pretty much all these real life problems, we want to leave a little bit of space here that we can see such that we can track what this value is. Same thing for our x-intercepts. The reason we ended up making this -10 for y, or that we left some space down here that was visible, is when we look for our x-intercepts, it makes it impossible. If I set this to 0, then solving for our x-intercept, we would have to like go outside of the graph, and we don't want to be doing that. So we want to be able to see a lower right-hand side and an upper left-hand side such that when we type this into our TI calculators, we're able to figure out what this is. Now, for my Casio users, it's less important that we see this area below, but I would always recommend keeping a little bit of -x, keeping a little bit of -y. And then all we want to really adjust on these graphs is how far it goes to the right, or aka the x max, how far it goes up, or the y max. Okay, let's continue to solve here. What is the domain and range in this situation? aka how far left and right does it go for the domain, and then how far up and down does it go? Okay, let's write that in here. So starting off with the domain, and we're going to write it in terms of time because that's what's happening here. We're going to write curly bracket time such that, well, time starts at 0 when before they throw it at the 110, and then time will be greater than 0 but less than, in this case, 6.78, which was when it hits the ground. As long as it's between there, the time can be any number that is in the real plane, because realistically there's an infinite number of ways to break this continuous graph apart or break apart the continuous time. Now for the range, very similarly, just a little different, we're going to write it as h of t, representing the height due to time, is such that it starts at 0, or not just starts at 0, but its lowest point on the beach is 0 in terms of height, but the height must be greater than the beach level. It reaches a maximum height of 124.7, but it has to be lower than that. That was its very maximum height, or that was its peak in terms of how it gets thrown off the cliff. It reaches 124.7. Past this point, it starts going down to the ground or towards 0. But we also know, and instead of writing t is an element of the reals, we want to write h of t is an element of the reals, because the height can be any sort of infinite combinations as long as it's between 0 and 124.7. Okay, there's our domain and range, or what we would call in our other lessons, the restricted domain and range, because normally with these functions, we just said t is an element of the reals or x is an element of the reals, but in this case, in real life, we have to fix our parameters so that it actually makes sense, because we don't want to have negative time, that wouldn't make sense, and we also don't want to have negative distance, meaning it goes through the ground, that wouldn't make sense either. Okay, now in terms of moving on to this next section where they say determine the height of the stone after each time, well, what we want to do here is the following. I'm going to write out these instructions just as I've done before, but I'm just going to do them off to the side here. Let's start with the TI. If I want to figure out what is the height given a certain time or given a certain input, I want to do this in the TIs. Second, trace, and then right on the very top, it will say value. Value is symbolic of if you have a certain x value, a certain input, you're going to plug it in. So when you do second trace value, you're going to type in both of these times and it will give you some sort of output or some sort of output height. For my Casio users, you're going to click Shift, G-solve, and then you might have to arrow over. So I'm just going to put that in brackets. There's a little arrow. If you need to arrow over, what you're going to be looking for is you're going to look for YCal or Y calculation. When you type in Y calculation, it's going to ask you or prompt you, what is the X value you want to solve at? Or what is the time value you want to solve at? You're going to type in these two here. Now, what you should find is the following. The height at 2.4 seconds is equal to, rounded to, actually I'm going to hold on to a couple decimal places here. You'll get 122.576 meters in the air. And then for when it's 6.1, you'll end up getting a height that is equal to, I got 31.371. Now, again, they'll ask you to round to specific digits typically when you solve these, but we're okay to hold on to a couple. Now, at what time is the stone at each height? This is an opposite way of asking. So what instead they're asking is, instead of typing in a time, now we're going to type in a height and figure this out. Now, for my TI users, you have a bit of work to do in order to get the solutions here. What I'm going to do is have you do the following. You're going to want to type in into Y2 the 115, or this the Y value they were looking for. So they're saying at this height, what is the time? In Y2, I want you to put in 115. In Y3, I want you to type in 60. Now we're actually going to show that above here. If I go up to my y2 and y3, we're going to type in 115, we're going to type in 60. Now, here's what this actually does for us. On the graph, you're going to see the following happen. At 115, there's going to be a horizontal line. It's going to kind of look like this. At the 60, it's going to have a horizontal line like this. Now, here's the thing I want you to notice. There is two positions of intersection. There is one here, there is one here, meaning at 115 height, there is two times in which that occurs. At the 60, there is only one time that occurs. So realistically, I could put like dotted lines down here and say that's one of the times, that's the other time, and that's the other time. We have three separate times in which these heights occur. So two for 115, one for 60. Okay, let's go down here and let's make sure we enter this piece in here. And I'll provide some instructions here of what we actually want to do for this. For my TI users, you're going to go second, trace, and instead of value, I want you to click intersect. When you click intersect, I want you to highlight over those intersection points and click enter 3 times. For my Casio users, you're going to click shift, Gsolve. You may need to arrow over. So again, I'll put the arrow in the brackets because sometimes it's on the secondary menu. And instead of clicking Y calculation like we did before, now you want to do X calculation, or given a certain Y value, what is the X? It will prompt you to type in a certain height or a certain Y value. From there, here's what I want you to do. For the first one, we know that there was 2 different times in this which this occurs. The first time was equal to 0.53 seconds. There we go. And then our second time was equal to, and I actually think this one was a little bit different. I want to make sure I get this correct. I believe when we did this in class, we ended up getting 0.32 seconds. So I just want to make that edit there. Hopefully if that's wrong, you correct me again, but I believe this is what we got. Our secondary one was 3.15 seconds. So these are the 2 points in which at 0.32 seconds, I'm at 115 meters. And then on the opposite side, once it's reached its maximum and it starts to come down, after 3.15 seconds, it's again at 115. Now for our second one over here, we're going to write x is equal to time, which is equal to, at 60 meters, this is way down the line. After 5.37 seconds, we are on the opposite side of the parabola, almost hitting the ground. We only have 60 meters left before the ground, so about halfway from where we started. And so after 5 seconds, we are at 60 meters. Okay. Now, realistically, what we could do is go back here and just make sure we highlight all this important information. So it takes 6.78 seconds to hit the ground after originally launching. After 2 seconds, we're at this 122. 6 seconds, we're at 31. The times at both of these are going to be the following. And then in terms of the height, or the maximum height, we have 124.7. It takes 1.73 seconds to reach that maximum. And the maximum, or the starting height, I should say, is 110. This was our starting height, or our y-intercept for this equation. Awesome. Okay, so again, I tried to be as clear as I could with those written instructions. As we move forward, I'm not going to provide the written instructions anymore. I'm just going to simply give the values for these. And so I may verbally explain it, but I'm not going to rewrite them out for these next couple. Okay, example number 1. Given a quadratic function to model a situation, you're going to recognize this one again. We're going to deal with a perimeter equation. And when we have a perimeter equation, how do we solve for the maximum length and width and the maximum area that goes with that? Now, we could complete the square, but in the case of using quadratic functions and in general form, we're actually going to graph this. So let's create a situation here. Whoops, I'm going to go back here. So a children's music festival, they want to rope off some sort of area for stroller parking. So the moms want to drop off their strollers so they're not lugging these around. They want to create an area. They have 160 meters of rope available to create this perimeter. Let's write the quadratic function that goes with this. So to do this, here's what we're going to do. We're going to generate a rectangle, or the rectangular area that the moms can drop their carts off, or the dads, if they're going. Now, what we're going to do is we're going to put a width here and a width here. We're going to put a length here and a length here. Now, they've told us right off the hop that the perimeter is equal to 160. That's the most amount of material we have, and it has to be divided amongst the 2 widths and the 2 lengths. Okay, we also know that the area of this rectangle is simply just the length times width, or the height times the base. Okay, we want to isolate one of these variables because we don't like the double variable. Just like when we were completing the square, we don't like the double variable in these equations. To do this, what I'm going to do is I'm going to take the 160 and I'm going to set it equal again to the 2w plus 2l's. I'm going to isolate for the length, so I'm going to subtract away the 2w's. There we go. Perfect. This is going to give me 2 lengths is equal to 160 minus 2w. And then just be very careful of this. I saw lots of people on the quiz or lots of people on test questions or even assignment questions, they double divide. So what I mean by that is they take divided by 2 because there's a 2 on the L, and they also divide by the 2 on the W. You only need to divide it one time, because here's what happens when you divide it the first time. 2's go away, 2's go away. 160 divided by 2 is 80. So it's already gone. You don't need to double divide that 2. It's a common factor that has already been eliminated. Now this is going to give us length is equal to 80 minus the W that remains. Okay, now we want to generate our function using the area. So we're going to go over here and say, if all of this was step 1, which was setting up the overall equation or getting the information required in terms of its equations, now for step number 2, to actually get the equation, we're going to write it as area, which is equal to length times width. Area is equal to, instead of length, it's going to be 80 minus W, all multiplied by W. This gives us area is equal to 80W minus W squared. I'm going to rearrange this in descending order. So it's going to be 80, or A, sorry, is equal to negative W squared plus 80W. And then because our calculators don't read things in terms of W's, we want to make this in terms of X. It's actually a really easy adjustment. Instead of W, I'm going to write negative X squared plus 80X. There we go. Here's our function that represents the overall area of this situation. Perfect. Okay, now moving forward, sketch the graph based on this. Now what we're going to do is, in order to sketch this, we're just going to plug this into our y1. Or if you have a Casio or TI, very, very similar. This function here goes y1 is equal to, you're going to plug in everything you see here. Let's make sure to write that below as well. It's going to be negative x squared plus 80x in for y1. Now, when we do this, here's what the graph is going to look like. Well, realistically, we're going to have to play around with our window settings as well. So let's do that as well. In the window settings, in your notes, I would always recommend writing X in the first one, Y in the second one, because it's not labeled in this case. Now, we're going to keep it very similar to last problem. I just want to keep a little bit of the negative X's, so not much. I want to keep the scale as 1. For the Y's, I want to reveal that there's a little bit below the X-axis, but I also want to keep the scale at 1. All we're going to do is play around with the maximums. In the case of this one, we look at this and we're like, they're supposedly telling us that when we go up here, the perimeter is constructed of 2 widths and 2 lengths, and the total is 160, meaning there's no way that the X max is going to be greater than 160. So realistically, what we can actually do is maybe even just set it to 100. Why not? Because we know that there is a combination of the lengths and widths coming together that make the overall 160, but one of these individual lengths and widths is not going to be greater than 100. That would be totally off. Now the y value, the unfortunate thing about this one is typically what I would do is I would go to my equation and be like, whatever the constant value is, or whatever the thing without the x, that determines kind of like a little bit about what we can do for our maximum. In the case of this one, it's not as nice, so we have to use a bit of approximation. What we're going to do is we're going to set this to 2000, and the reason is because we're going to think about it in terms of, if I have area that is constructed from 160 meters of fencing or 160 meters of total material, it's going to be something in the thousands. You're going to have to play around with it a little bit, but you can easily pick up on this in the sense of, if your graph isn't high enough, the graph would look like this. And I'll actually use my border cutoff as a way to show this. It would look something like this. And if you see a graph that looks like this when you originally plot it, it just means increase your y maximum. So anytime you see that, just be like, hey, I haven't increased my y enough. Keep increasing it until this gets lower and lower and lower, and then eventually it will all be in the picture. According to this window settings, though, this is the perfect window settings for us. We want to generate our x and y axis just like this. If our maximum is 2000, I want you to go over here and write 2000. If our maximum on the x is 100, I want you to write in 100, just so that we can kind of see the endpoints of our graph here. Now what we're going to do is we're going to plot a couple points based on the graph. One of the points is actually 0, 0, and you're probably thinking, like, how do we know that? Well, if there's no c value, or aka if the c value is non-existent on the function, there's no constant value, you know it starts at the origin because the c value is representative of the y-intercept. Technically, if I really wanted to, I could write in plus 0 if I wanted to. So we're going to put a dot right at 0, 0 and represent this is our first point, and I actually want you to write it as an ordered pair. 0, 0 is the ordered pair in which this starts. Now, graphically, once we type this in, we're going to do the following steps. Again, for my Casio users, you're going to just click Shift G solve maximum. For my TI users, you're going to go second trace maximum. And when you do that, it's going to enable you to build out the following graph. And I'm just going to draw a very, very rough sketch of this. It's going to come up, and then it's going to come back down. And that might even be too high. I honestly think I'm just going to redo this and just draw it just a touch lower. So here it is, and then right about here. Perfect. Now, when we do this and when we figure out our maximum, for my TI users, you don't have the luxury of just pressing a button and getting the automatic max. You have to go a little bit left, a little bit right, and press enter on both of these. And then the guess, we want to put our guess somewhere about right at the peak here. Now, when we do that, we're going to put a dot here and say that our vertex point, or our P and our Q, is when it's 40 for the X value and 1600 for the Y value. And this should be given to you by your graph. Okay, now this is the coordinates of the vertex, so we can actually answer the first question here. When they say, what are the coordinates of the vertex? Well, let's write that as P and Q. So P and Q, which is 40 and the 1600. What does the vertex represent in this situation? Well, we know that the X was symbolic of the W's. Remember when we made that original substitution up here? We said instead of W's, our calculator will read it in terms of X. That means that whatever X value we just solved for, or in this case the P value, this represents the overall width. So the width is 40 meters. Now, the nice thing about this problem as well is not only is the width 40 meters, but because it's two lengths and two widths equals 160, that actually means that they're equal to each other. So this is more of like a square area than anything. We can also say the length is 40 as well. Now, this isn't always the case, but in this specific problem, because there's two lengths and two widths, and they total to that 160, this case, we're going to say that they're the same. Now, from here, what we're going to do is we're going to write it as if the width is 40, the length is 40, the 1600 represents something specific, or the Q value, the 1600 is the maximum area. Area is 1600. And we want to make sure we have the right units, meters squared. There it is. Okay. Now, let's make sure we highlight those answers just so that you have them stored for yourself. Excellent. Now, in the next part, determine the domain and range. There's something that's actually missing here. In these problems, we're always going to want to solve for 3 following points on the graph, and let me make sure I emphasize that. Just like in the last problem, we always want the y-intercept. In this case, our y-intercept is 0, 0. We want our maximum point, or the highest point. Sometimes it's the lowest, but in the case of this one, we're going to say it's a maximum. And then we also need the x-intercept, or more than one x-intercept depending on the problem. But for this one, we're just needing that one x-intercept that's down here. I want you to put a dot here. And again, when you're solving this, if you have the Casio, it's Shift G solve 0, which will give you this value automatically. If you have the TI, you're going to have to go second trace 0, which is number 2. You're going to want to go a little bit left, press enter, a little bit right, press enter, and then when you guess, try and bring it as close as possible. Now, when we do this, this is what it's going to give us. We're going to get 80 and 0. Okay, so we have an x-intercept. We also have a maximum point. We also have our y-intercept. Those 3 points are so critical for us. Now, let's go down and describe our domain and range. Using the domain, or all our possible x values, we say x such that, well, the lowest possible value for x was 0, or the origin, but then it must be greater than, or x is greater than that 0, but strictly less than, or I shouldn't say strictly, because strictly means just purely less than. It's less than or equal to the 80, which was our x-intercept, but there can be any sort of real number combination that exists between those. There's an infinite amount of solution types. Real number, or the range, sorry, not the reals, seeing too many R's on here. The range is where y such that it starts at 0 because it starts at the origin, and the maximum value, which is our Q value, was at 1600. So the area can either be 0 or it can be 1600 for here. And then we're going to say that y is an element of the real numbers. Now, I'm going to have us edit something very, very particular here. On this side, specifically with area equations, I almost want to knock these out and just put in the following: greater than, greater than. You're going to see why in just a second, because we're going to have to justify this, or we're going to have to explain this right below. But I want you to do this in terms of the domain and range. We want it to strictly be greater than zero, because if it's strictly greater than zero, that actually implies a very specific thing, and it is something that we need in order for this problem to make sense. Okay, identify the assumption you made. The assumption we made is tied to that domain and range where it's strictly greater than zero for both of these. We cannot have, or we want to have, a width slash a length that are not equal to zero. Similarly, not only do we want the width and length to not equal zero, we also want the area that is not equal to zero. So therefore, our domain and range is strictly greater than zero, because if they were zero for either the y or the x, it would mean the area is zero or the width and length is zero, and we don't want to have that. So our assumptions is just to keep these away from zero, because that would be inappropriate for this. Okay, and then again, what we can do is we can highlight our domain and range now that we have them here. All right, let's go on to example 2, which is a revenue problem. Now, I recommend getting your highlighters out. The reason I say get your highlighters out is because it helps you organize this information in a very nice way, and we're going to show that right here. When we deal with revenue problems, they always are comprised of price and quantity multiplied together. Now, let's read out the problem and then go from there. The cost of a ticket to a hockey arena that seats 800 people is $3. So we have an original quantity of people and original price. At this price, every ticket is sold, meaning they've sold out. The arena manager then gets a little greedy and says, well, let's see if we play around with the price. If we increase by $1, then supposedly by market research, attendance falls by 100 people. So, even increasing it by $1 is enough to like steer a ton of people away, which is kind of unfortunate, but that's just the way the problem is. What I would like you to do is with one of your highlighters, let's highlight everything related to the people. There's originally 800 people, but they say attendance will fall by 100. Pair these two things together. The other two things I want you to pair together using a different color are the price. It starts at $3, but for every dollar increase, we see this decrease in attendance. Write the quadratic function in terms of R, or the revenue, where X is the number of price increases here. So they're actually nice. They actually tell us what our X represents, but let's make sure we put this together here. We're going to say that the revenue is equal to price multiplied by the quantity. Perfect. Now, if it's revenue equals price times quantity, then what we're going to do from here is we're going to put together our brackets. And I always recommend just writing in like kind of a template here of one bracket, the other bracket. They told us the price originally starts at $3. And that for every increase, or every increase in by $1, we see that the attendance falls. So this takes care of, and I'm going to highlight them just to keep the color coding going on here. If it was blue, I'm going to highlight this piece blue, just to show you that the information is being pulled from the problem into the brackets. The quantity, it starts at 800 people. So I'm going to write 800 as the first value, and it decreases by 100, but we don't know how many units of 100 it decreases by, because it also depends on how many times we increase the price by $1. So just to provide some clarity around this, because on the quiz, this was one thing I wanted to make sure we're very straight on in terms of we're not confusing this terminology here, or this concept. When you talk about the X value in these revenue problems, whether you're completing the square or doing these things graphically, the X is the number of price changes and the number of groups of people changes. It's not actually the price itself or the number of people that's changing. It's simply just the number of price increases that are happening. So it's more of a reflection of how many times do we increase by $1? How many times do we decrease by 100? It's not either the price or the quantity. So be very careful with that. Now that we have our nice little color coding system here, this actually makes it really easy to pull information from the problem into there, and we can kind of ignore a little bit of the context and just strictly get to the numbers that we're actually interested in. Now let's expand this out here. When we expand this, here's what we're going to get. 3 times 800 is 2400. 3 times negative 100 is negative 300, not negative 100. There we go. And negative 300x. This is going to be 1 times the 800 is 800x. And then lastly, 1 times negative 100x, this will give us negative 100x squared. Now we're going to collect our like terms and rearrange this. So I'm going to put the negative 100x squared, or our largest power, first. I'm then going to put negative 300 plus 800 is plus 500x in the middle. And then we're going to put our 2400, or our constant value, on the end. And this represents the revenue. Perfect. Okay, so we're going to highlight this, representing that this is the statement we want to type into our calculator. Now, let's actually do that below here. In terms of y1, I'm going to take exactly what we just wrote there and write it here. So we're going to say that revenue is equal to negative 100x squared plus 500x, which is our middle term. And then we're going to write it as plus 2400 on the end. When you type this into your y1, either using the Casio or the TI under your graphing or your y equals mode, this will allow us to sketch the graph. But what we're going to realize is that the window settings are really off. So we got to adjust those window settings so that they're appropriate here. What we're going to do is right below here, I just want you to write in an X and a Y, representing that we have our X window settings, our Y window settings. And again, just like we did in the previous problems, because there's going to be no such thing as like negative revenue, they're not going to lose money on this event. We don't want to go necessarily too far below the y-axis, and we want to think about this being in quadrant 1. And in terms of price and ticket sales, I mean, realistically, there could be a price decrease, so that is possibility. But realistically, to maximize revenue, we're probably going to see a price increase. So what we're going to do is let's put in -5, just like we did before for the minimum for x. I want you to keep the scale as 1. I also want you to keep the scale as 1 for y as well, and put this as -10 so that we can see a little bit below the x-axis. So what you're going to notice is these are very familiar. We haven't actually changed any of these values in all the problems we've done. It's always the maximum values we change. Now for price increases, think about this logically. They told us in the problem that for every dollar we increase it by, we lose 100 people, meaning they can't actually alter the price that much. What I'm going to do is in the x maximum, I want you to write this as 10. There's no way that they do more than 10 price increases, or else they won't sell any tickets, which that would mean they lose all their revenue. In fact, they go negative if they're going to, decrease or increase the price a certain amount, because then nobody will go. Okay, the y value, we can use our constant value to help us judge this. Remember that the c value, which is here, is an indicator of the y-intercept. If this is our y-intercept, and I'm actually going to write that in here, this is representative of the y-intercept. If this is our y-intercept, let that use as a guide for how high you need the graph to be. Realistically, the max has to be greater than this, because this is kind of like that break even, or that, not break even, I should say, but it's that entry revenue they would make. So if they sell the tickets for $3, they will have 800 people go. This is kind of the baseline. The maximum is going to exist somewhere higher than this. I'm just going to go 1,000 greater than that. So I'm even going to make this like 3,400, just so that it's a little bit higher. And just in case it approaches something that's $1,000 more of revenue, at least we'll have it upwards here. And again, if you see a graph where it looks kind of like this, what I'm going to draw on my laser pointer, if you see that, just adjust your y value so that it's higher, so that this gets lower and lower, and eventually you'll be able to see the whole picture there. All right, now using these window settings as the x, min, max, scale, and same thing for the y, we're going to draw it out here. So here's what this is going to look like. We're going to have our y-axis here, our x-axis here when we sketch it, and I'm going to provide some parameters here. So first and foremost, we said that our maximum y value is 3,400, so the highest point we'll see is 3,400. The farthest side over here is going to be 10 for x. And then the sketch of this graph is going to look like the following. We're going to sketch it in, and it will kind of have this look to it. Very, very similar to something like that. And then again, I'm forgetting to use the sketch tool. I want to make this as neat as possible. So let's aim to do it something like this. Perfect. This should roughly be about what your window settings will give you in terms of the diagram. It might look a little larger, a little smaller, but within this range. Now, what we're going to do is we figured out the sketch. So here it is. But this isn't a ton of information. What we want to do is, first of all, let's plot our y-intercept if we know it from here. That's our c value. Our y-intercept, which is the c value, is 2400. So I want you to put a dot here. And then once you put your dot on the y-intercept, you can write this as 0 for x, 2400 for y. And if you need to, just make sure you draw an arrow to that point, representing that that is the point we're talking about. We then want to figure out our vertex for this, because in parts, in the next part here, we actually want to know our vertex to help us out with the remainder of the situation. So to determine this, in our calculators, if you have the TI second trace maximum, you'll do your left-hand side, click enter, your right-hand side, click enter, and your guess down the middle. For my Casio users, shift G solve max, it gives you the coordinate right away. You're going to end up getting that it is 2.5 and 3025. Okay, excellent. The other thing I'm going to want to get here is not only can we get our vertex, we can get the x-intercept. The x-intercept, second trace 0, and you'll repeat the left-hand side, which is here, right-hand side enter, which is here, and your guess, which will be right towards the point, as close as you can. For my Casio users, you're going to do shift, G solve, and 0, and it will give you the coordinate right away. We end up finding that this is at 8 and 0. Now that we have these points, we have a vertex point, we have a y-intercept, we have an x-intercept. These 3 points are more than enough for what we need. We just need those 3, and commonly you're seeing that we just need those 3 in pretty much all the problems. All right, let's use this information to help us solve the rest. What is the domain and range? Well, we know that the x values start at 0 and they go to a maximum of 8. So we're going to go over here and say the domain where x such that starts at 0, it's greater than 0, but it's also less than or equal to 8. Anywhere between is an acceptable answer on the real plane. The range, we're going to write this as y such that it starts at 0. We can technically make 0 money, and then it must be greater than 0, but it's less than the maximum, which is 3025. And then as long as it's between there, realistically, we could break down this maximum revenue or this revenue into infinite combinations, because depending on what we sell the tickets for, there's going to be a totally different revenue that goes with that. Determine the maximum revenue and the number of price increases in order to reach this maximum revenue. Well, those come directly from the graph. It's our P and our Q. Our P, or this value here, the 2.5, is the number of price increases. This represents the number of, or our maximum revenue. So let's make sure we write that out here. The maximum revenue, which I'm just going to short form as max rev, is equal to the Q value, or the vertex value for the y, which is equal to $3,025. So this is our maximum revenue. Our maximum price increase, or the number of price increases to be more specific, the number of price increases is our, and I'm just going to write it as very similar format to what we just did there, is equal to the p value, which is then equal to 2.5. So that's the number of price increases we can make, is 2.5. Now, using this information where we know a maximum revenue and the number of price increases, given that that's our value for p, or if we even want to put it here, this is our value for x, that will allow us to go back to the original price and quantities and actually solve for what is the price given this maximum revenue and what is the new attendance given this revenue. Okay, the price, let's pull this statement from our first part here where we set up the equations. Price was equal to $3 plus however many dollar increases we make. In this case, that's 3 plus 1 times the 2.5, which then therefore will give us a price equal to 3 plus 1 times 2.5. This is the same as saying the price of each ticket is $5.50. What is the new attendance? Well, that's the quantity marker. Quantity was 800, which is the original attendance, minus 100 times the number of price increases. This is going to be equal to 800 minus 100 times 2.5 is 250. This is going to end up giving us 550. And so let's make sure, I'm going to even write it in the very similar format just to keep everything uniform. The quantity of people that go are 550 people.
And I'm going to phrase it as 550 people attend, just to keep it all nice there. Okay. And then we could even write up here, this is $5.50 per ticket. Just to be even more clear, I think clarity is important in math, especially in these word problems. And let's just go through and highlight everything that we've went through here. So first and foremost, domain, it's contained between 0 and 8. We have our range. We go down to our maximum revenue, which is our Q. Our maximum number of price increases is always that X value at the vertex, which is our P. Our price per ticket to maximize revenue is $5.50. And unfortunately, to maximize revenue, we're going to see a decrease in the number of people. So we're no longer selling out the arena, but we are maximizing revenue, which is something that is very real to many pro teams. All right, now we have one last problem here, and it's this area and perimeter problem where you're going to recognize it as a complete square problem. But in this case, again, we're not completing the square. We want to make sure we write this in terms of, let's make sure we can generate a function in general form, plug it into the calculator, make the right parameters in terms of our window settings, and then solve. Okay, let's draw a diagram of what's happening here. A rectangular lot is bordered by one side where it's a river, and the other three sides have 600 meters of fencing to box it in. So the rough sketch that would look like the following. Here is the river on the one side, and then on the other three sides, we're going to have some sort of width, some sort of length, some sort of width. And so I'm going to classify this as the width and make that a touch neater here. Here's our width, here's our length, and here's our width. Now, realistically, if you swapped width and length in terms of their labels, that's okay. You'll get the exact same value in the end. Your length and width will just be opposite in value, but that doesn't actually mean that they're opposite. It just means your labeling was opposite, which totally fine. Okay, here's our sketch. One of the sides is bordered by the river, so we don't need to use any material with that. Now, in terms of width, write an expression for this in terms of x. What we are going to have to do is perimeter, which is equal to, we have 600 meters of total material. It includes 2 widths and 1 length. If we isolate this for length, we're going to subtract 2w from both sides. And this is going to give us length is equal to 600 minus 2w. We also know that the area is equal to length times width. If area is equal to length times width, then we can write it as A is equal to 600 minus the 2w. Let me just make that a touch neater there. Times the w that's on the outside. So we've substituted everything in that was representative of the length into the length of the area statement. Area is equal to 600w minus 2w squared, because we multiply a w into each of these. Now we want to write it in terms of descending powers. So we're going to write 2w squared plus 600w. Now when you look at this, you're like, wait a minute, we can't put w's into our calculator. So let's do what the instructions said and write the area in terms of x's. We're going to make w equal x. So instead of w, I put w squared is x squared, and then 600w, instead of w, it's going to be x here. There is the function we can type into our y1 of both the Casio and the TI calculators. So let's take a second to just write that in here right below. We're going to copy exactly what we see here. In y1, it's going to be negative 2x, and I actually think we have enough space up here, negative 2x squared plus 600x. Now, unfortunately, again, this one doesn't have a constant value, which affects our ability to determine the y-intercept right away and build out a window setting based on that. But we can use a little bit of logic here in order to help us with our window settings as we type this in. Again, put x and y below the two brackets here. Oftentimes they'll be labeled for you, but if they're not, just label one as x, the other one as y. What we need to do is we need to use a bit of approximate thinking here. What we did in the past few problems is we always set our x value to -5 for our minimum and our scale to 1. We're going to hold true to that. For our y, we're going to make this -10 and 1, just like we did in the other problems, to hold true to it, because realistically, we know that the area will be maximized with a parabola that goes through quadrant 1. That's just the way that these real world scenarios go. They don't always have to be in quadrant 1, but I mean, we're talking about numbers that, whether it be area, lengths, price, and quantity, they all have to be these positive values typically. So we're always going to typically be in quadrant 1. This holds us to it. The only thing we need to adjust is our x max and our y max. Now, to help provide a little bit of context in terms of what our x max could be or what our w max could be, we look at this and we're like, there's only 600 meters of material, meaning it has to be split between these 2 widths and 2 lengths, or these 2 widths and 1 length, because the river borders the one side. So I look at this and I'm like, if it's split amongst all these things, I'm going to set my domain, or I'm going to set that x max to something like 300. I think 300 is more than enough. Maybe even let's just set it to 350 just to be safe here, just to include a little bit more space. Because neither the length or the width are going to be greater than this 350. There's no way based on the combination having to add up to be 600. Now, in terms of Y max, this is where you're going to have to do a bunch of guess and check, because you're going to get, probably under the original settings, a graph that looks like that. You won't even be able to see the maximum. So if you have a graph that looks like this, keep increasing the overall Y max. Similarly, if you got a graph that looked like this, what that means is that you have to increase both your X's and your Y, because you can't see where it came down over on this other side. If you cannot see this side, or you can't see the maximum, it means you have to adjust both. What we're going to do is we're going to set it equal to 50,000, just to be very, very large. And you would find this through trial and error, but we need to realize that the area is going to be quite large. When we have a perimeter value, or a perimeter that can equal 600 meters, our area is going to be quite large. So don't feel free to just increase, play around with it a little bit until you get something that fits. In this case, 50,000 will probably do us the trick here. Okay, now here's what the sketch is going to look like based on that. Again, we're going to have something in quadrant 1. We can write our y-axis, our x-axis. This is going to be, for our maximum point, we said that it was, for the y values, a maximum of 50,000. So up at the top, I'm going to write this as 50,000. And then in terms of the x max, we said this was going to be equal to 350. So I would just always write in those outer bounds of y and x just so that you can see them. Then the sketch is going to look like the following. If there's no constant value, remember, there is no plus c over here, or theoretically it is 0. And if the constant is 0, this is another way of saying that it starts with a y-intercept at 0, 0. So you can sketch this in right away. Let's make sure to label this 0 and 0, and arrow to it. All right, now when we sketch this in, it's going to kind of have this form here. So it looks like about this, and then it comes back down like so. Now, this might not be a perfect sketch of it, but it does the trick. Now, what we want to do is we want to get our maximum in this case. In order to determine the maximum, second trace maximum in terms of the TI on the Casio, shift G solve max. And when you do that, here's what you're going to get for this. It's at 150, which is our P value. It's at 45,000 for our Y value, or our Q value. The other piece we're going to want to get, just like we've done before, is if you have your y-intercept, you have your p and your q, or your vertex, we want to solve for this x-intercept down here. Put a dot here. On the Casios, you're going to go shift G solve x-intercept, or in most cases, shift G solve 0. It will give you the value right away. For my TI users, you're going to go second trace and 0, which is number 2. And you're going to go left and enter, right and enter, guess right above the point. Now, when you do that, it's going to give you an x-intercept of 300 and 0. Okay, now we have our furthest left point, we have our furthest right point, we have a maximum point. This is going to help us not only determine domain and range, but all the information that might be asked past this point. What is the maximum area of the lot? It's the Q value, so it's 45,000. Maximum area is 45,000. And not only 45,000, but using the units of the problem, this is meters squared. Perfect. So there we go. We can highlight this piece here. What are the dimensions that produce the maximum area? Well, we know the width. Because x was equal to the width, and the p value is technically the x value, which is then the width, we look at this and we see them as all a connection. W and x's, the w is right here, it's our p value, so our width is actually 150 right away. We can write, therefore, width is equal to 150 meters, which is equal to the p value. So that's one piece. We can highlight this. Our length was generated from the following statement. Length is equal to 600 minus 2 times the width. That's the same as saying 600 minus 2 times 150. 2 times 150 is 300. Therefore, our length is equal to 600 minus 300, which is equal to 300 meters. There we go. Now, if you wanted to confirm these are it, plug them back into the perimeter equation, and that will give you these exact values here.
Now, again, they could always tack on the domain and range to this if they really wanted to. They could ask about an x-intercept, saying what width or length is there in terms of the opposite, which we could easily see here. They could say, like, technically, if we want to have zero, I mean, if we did a domain and range just like the previous one, if we're talking about something that is anything area driven, you wouldn't want to say that the domain and range includes this point, because then you're essentially saying that the width and length and area are zero, which I don't think that's appropriate for this. So in this type of problem, this is almost like an excluded point here, and we should almost be just purely thinking about our maximum point here and what that means for us. All right, you are going to want to make sure you get the practice. Please go on to the assignment from here and see how you do. If they ask you for anything graphically wise, do it on grid paper. We have some grid paper in the classroom, or if you have your own grid paper, great, but do as many of these as you can, because you want to get practice with typing these into your graphing calculator, especially because there wasn't any visual examples in this. Rather, we just provided the verbal explanation with a couple written notes regarding what buttons to press. You need to get comfortable with those buttons. All right, good luck with the homework.